So this is from 2 chapter 1, patterns and sequences. So here's the first question, 13579. What we want to do is we want to find the pattern. Let's look at this real quick. 13579. The numbers are increasing by every term. But what pattern is it increasing in? Well, what's the difference between 1 and 3? That's 2, because 1 plus 2, that's 3. The difference between 3 and 5 is also 2. And 5 and 7, same thing. And so since it's plus, the operation for this is going to be plus. So I'll just write it here. So the second question, 2, 4, 6, 8, 10. It's like this one, increasing. The difference between 2 and 4 is 2, again, like this one. So add 2 to the previous number. And the operation for this is also going to be plus. So it's the same thing, but what's the difference between them? Well, it's the numbers 1, 3, 5, 7, 9 and 2, 4, 6, 8, 10. And there's actually another pattern hidden between 1 and 2 separately. There's another pattern 1 and there's another pattern 2. So I want you to figure it out. Got it? So 1, 3, 5, 7, 9. What you may have noticed is that these are all odd numbers. 1, 3, 5, 7, 9. So this is an odd number pattern. And these 2, 4, 6, 8, 10, they're all divisible by 2. Or in short terms, even numbers, yeah. So this is going to be an even number pattern. Okay, now let's look at the third question. 27, 24, 21, 18. What can you get from this? Unlike the previous two, it's decreasing actually. The numbers get smaller and smaller. I'll give you some time to figure this out. And by some time, I mean 1 second. Yeah. So, I'm pretty sure you've already figured it out. The difference between 27 and 24. And the difference between 24 and 21. They're all by 3. And they're decreasing by 3. So therefore, it should be subtract the previous number by 3. So like 27, 24, you minus 3 from 27, you get 24. 24, you minus 3, you get 21. 21 minus 3, you get 18. So, the operation is going to be minus. Now the fourth question, 2, 6, 18, 54. First term, 2 is just 2, but the fourth term is already reaching 54. That's quite a lot, and it's growing by quite a lot, and it's growing not really at like a set speed like 1 plus 2, 3 plus 2 again. No, it's increasing, but the operation here is definitely not plus, something bigger. And I'll give you some time to figure this out. And by some time, I mean 1 second. There. I'm pretty sure you've already figured it out. It's increasing exponentially. And by exponentially, I mean like multiplying it by 2 every time. Yeah. So 2 multiplied by what equals 6? Of course, 3. 6 multiplied 3 will equal to 18, and 18 multiplied by 3 equal to 54. Yeah. So therefore the pattern should be multiply by 3. Okay. There we go. Now let's look at number 5. 1024, 512, 256, 128. It's decreasing and at an alarming rate too. So it's not decreasing at a set speed like number 2 here. It's decreasing exponentially, as you would call it, and as you've already figured it out, the operation for this is going to be divide. So of course, 1024 divided by 2 is equal to 512, and divided by 2 again, you get 256, divided by 2 again, 128. So therefore the pattern for this should be divide previous number by 2. So that's it for all these basic patterns. But now we'll be looking at the 6, 7, 8 and 9 question. Here's the 6th question, 4, 9, 16, 25, 36. What can you get from this? Well, it's definitely not plus, I can tell you that. It's not increasing at a set rate. But then again, it's also not really increasing exponentially. So what's going on here? You might say there's no pattern and that this is just all random. You will be wrong, because this is actually has a pattern. So I'll give you some time to figure this out, because this one is actually kind of complicated. Not really, but yeah. I'll give you a hint. 4, 9, 16, 25, 36. It has something to do with the power of 2. It's actually a perfect square pattern. So for example, this 4 right here is actually 2 to the power of 2. This 9 right here, 3 to the power of 2. And 16, 4 to the power of 2. 25, 5 to the power of 2, and 36, 6 to the power of 2. They're all perfect squares. Therefore, it should be called the perfect square sequence. And if you're wondering what this thing is right here, it's actually one way to write a number to the power of 2. So for example, like 7 to the power of 2, you could write it as this, or you can write it as 7 to the power of 2, like this. Yeah, but let's get back to the main topic. So therefore the pattern of this should be perfect square pattern. Okay, so let's say you were to apply the same logic for number 7, except on a different power. Yes, I'm sure you've already figured it out. If you haven't, that's okay. Don't push yourself. This is actually a perfect cube pattern. So for example, 8, 2 to the power of 3. 27, 3 to the power of 3. 64, 4 to the power of 3. 125, 5 to the power of 3, etc, etc. This is obviously going to be to the power of 3. And so this will be a perfect cube pattern. Okay, now let's look at A. It looks kind of random. So 12, 25 is increasing at first, but then it's decreasing. 24, decreasing again, 5, but it's increasing again, 36, but it's decreasing again, 1. Well, this actually does have a pattern, but it's very different from the first to the 7th question. So for the people who haven't figured this out, I don't blame you because I don't think you've ever seen a pattern like this before. These are called alternating patterns. So like, let's look at 12, 24, and 36. What can we get from this? They're all increasing by a certain amount, which is 12, obviously. So plus 12 and 24 plus 12, that's 36. Now let's look at 25, 5 and 1. They're increasing exponentially. So this will be the divide by 5, because 25 divided by 5 is 5 and 5 divided by 5 again is 1. So there you have it, plus and divide, the two operations. Okay, here we go. So now let's look at the 9th question. It has the same logic as the 8th question. Now I'm sure you've already figured this out. If not, go for it. So let's look at the first, third and fifth term. What do these three have in common? It's that these are all perfect cubes. You may have noticed this already. So 216 is going to be 6 cube. 343 is just going to be 7 cube. And 512, 8 cube. And now 2, 4 and 6 plus 2 to the previous number. So therefore should be, and of course operations for this will be plus and power of 3. Okay, now we're moving on to the Fibonacci sequence and Pascal's triangle. Two very important patterns, or should I say sequences, in the mathematical world. So first let's look at the Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, 21, 34. Each successive term in this sequence is the sum of two previous terms. What does that mean? Essentially, the first term, which you can actually call T1, let's say, and then we have T2, wait. So T1 is 1, T2 is 1. The first term, which is this one, is 1. The second term for the Fibonacci sequence is also 1. The third term is 2. So what does this mean? It essentially means that the third term will actually equal to the first term plus the second term. If you're looking at something like this, essentially the complete way of saying this is the nth term is equivalent to the sum of the previous two terms. So the nth term is equivalent to the sum of the term n minus 1 and n minus 2 because they're both one term behind. And one term behind and one term is two terms behind. Yeah, so for example, it's equal to 2 and 1 plus 2 is equal to 3 and 2 plus 3 is equal to 5. Yeah, so essentially that's this Fibonacci sequence. And what's interesting is that the Fibonacci sequence can also be known as this diagram right here, known as the golden ratio. Something quite important in geometry. So let's look at it. This is actually a square with unit 1 right here. And there's another square with another unit 1 right here. And so the square above it will be consisting of two squares of union 1. So 1 plus 1 will be 2. 2 plus 1, 3. So it's 3 plus 1 plus 1, which is 5. And now you can repeat this. 2, 1, 5. That's 2 plus 1 plus 5. That's 8. And 8 plus 2 plus 3, that will be equivalent to 13. Yeah. So now that's the Fibonacci sequence for you. Now let's look at Pascal's triangle. The ones are dragging along. Right here. And what's going on here? So let's read this. A term in Pascal's triangle is obtained by adding the two terms above the said term. So what it means is, let's say you have this 2 right here, and essentially there's two numbers above this 2 right here, directly above it. There's 1 and another 1. So you will add 1 and another 1 right here. So 1 plus 1, that will give you 2. And you can do the same for, let's say, this number 10 right here. 6 and 4 directly above it. So 6 plus 4 is equal to 10. So therefore, yeah. This Pascal's triangle is quite unique because it has a lot of patterns residing in it. I'll only be going over 5 patterns in this Pascal's triangle. There could be more, but let's look at the first one. Powers of 2. Essentially, it's going to be find powers of 2, like the pattern of the powers of 2 in here. So let's look at the first row, 1, which, let's say, 2 to the power of 0. Let's account for 2 to the power of 0 in this first row, 2 to the power of 1 in the second row, and etc. So 2 to the power of 0, if I add anything to the power of 0, is actually equivalent to 1. Well, except for 0 to the power of 0. It's 0 to the power of 0 is actually undefined. Although if you want to define it, it's actually 1, but the ways of getting 0 to the power of 0, we're not going to go over that today. So just remember that anything to the power of 0, as long as it's not 0, is equivalent to 1. So there we go. So let me just leave a note right there. So yeah, there we go. So let's look at 2 to the power of 1. So 2 to the power of 1, as you know, is 2. But, okay, we have 2 ones here. And what you want to do is you want to take the sum of all the numbers in that specific row. So for example, there's 2 ones here, 1 plus 1, 2. Exact same answer. 2 to the power of 2 is 4. So let's answer 4 right here. Let's take the sum of all the numbers in this row. And of course, 1 plus 2 plus 1, that's 4. And you can do that for all the rows in Pascal's triangle. 16. Yeah, that's. So now we have now we have the powers of 11. Essentially, it's just going to be 11 to the power of whether 2, 0, 5, you name it. And let's do the same thing here. And let's skip all the way down to 11 to the power of 6 because there's some important stuff down here. Now, unlike the powers of 2, we're not going to take the sum of these numbers in a row. Instead, it's just simply right in front of us. So for example, 11 to the power of 0, as we said, anything to the power of 0, as long as it's not 0, will be equal to 1. And now 11 to the power of 1 is just 11. And as you can see right here, it specifically shows that number in that row. So that's 11. And 11 to the power of 2, that's 121. And as you can see right here, 121, 121. Yeah. And you can continue this with all the other rows. 11 to the power of 3, that's 1331. Don't believe me, plug it in the calculator. Yeah. But now, let's skip all the way to 11 to the power of 6. Now 11 to the power of 6 is going to be 1771561. It's going to be the answer for 11 to the power of 6. So let's look at this row right here. 1771561. But it's not equal to that. It's something different. But you can actually get the actual value of 11 to the power of 6 out of this. How do you do it? So, what you're going to do is you're going to go to the first 2-digit number from right to left order, and you see this this 1, you drag it over to the 20. So 20 plus 1 is going to be 21. 21, you take this 2 in front of the 21, you drag it over to the 15. 15 plus 2, that will be 17. And same thing, this 1, you drag it over here. 6 plus 1, 7. And therefore, you end up with 1771561. 1771561. Okay. Alright, so that's quite fascinating. Okay, so now let's look at the third pattern that's residing in this Pascal's triangle. Let me just, I'm gonna make space for the thing. Okay. Okay. So now let's look at the Fibonacci sequence. Yes, the Fibonacci sequence is in this Pascal triangle. So as you know, the Fibonacci sequence 1, 1, 2, 3, etc. Okay. So how do you find this Fibonacci sequence in this Pascal triangle? Quite obvious actually. Not really obvious, but let's say this thing right here. We'll draw a diagonal line over it. So yeah. So that will be the first number of the Fibonacci sequence, and we will do that the second row is again 1, and now let's drag it over to this side. That'll be 1 and 1. You captured 2 ones. And the sum of these 2 ones is 2, the third number of the Fibonacci sequence. So now the fourth number of the Fibonacci sequence is 3. So let's do the dragging again. 1 and 2. The sum of 1 and 2, 3. And you could go on. For example, 1, you drag this line and you get 1, 3, 1. The sum of 1 plus 3 plus 1, 5. The fifth term of the Fibonacci sequence. Yeah. So that's where it is. Just going to make way for the fourth and fifth pattern. Okay, now let's look at the perfect squares. I'm sure you know what perfect squares are already. 4, 9, etc. etc. I mean, you could always look here. Okay. So, how do we find a perfect square sequence or pattern in this Pascal's triangle? Well, okay. So let's say you want to find 2 to the power of 2. So to find 2 to the power of 2, you will let's say okay, so 2 to the power of 2, because 1 to the power of 2 and 0 to the power of 2. So essentially 2 to the power of 2. So what you want to do is you want to find like 1, 2, 3, like the third diagonal is the first one, is the second one. You want to go to the third one over here. Yeah. And of course, you want to find the 2 digits. No, in this third diagonal, you want to find this, the most up digit and the second most like high digit. So 1 and 3. So 1 and 3. The sum of 1 and 3 will be 4. It's 4, which is identical to 2 to the power of 2. It's not identical, it's equal to 2 to the power of 2. Now we can do that for 3 to the power of 2. Go here to the third diagonal again. And this will be 6 plus 3, that will be 9, which is equal to 3 to the power of 2. And you can keep doing that with like going down the rows. And now let's go for the fifth pattern and the last one for this video. The perfect cubes, the perfect cube pattern. Yeah, it's right there. 8, 27, 64, 123, 125, sorry. Okay, so perfect cubes, how you want to find them? So essentially, of course, I kind of messed up just now. That's why I cut the video. So what do you want to do? Let's say you want to find 3 to the power of 3. let's say that what you want to do is you want to find 3 numbers around it and form a triangle like this, and another 3 numbers around it, and will form like a star like this with the 2 triangles. And now you have to find the product of these 3 numbers that the triangles are connecting to, and same thing for the other triangle. So 1, 3 and 4, 1 times 3 times 4, that will be equal to 12, and 1 times 2 times 6, that will be equal to 12 also. Yeah. Okay. So what you want to do is you also want to plus this digit in it. So 1 times 2 times 6, for example, 1 times 2 times 6 plus 1 times 3 times 4, and want to plus the number that is cubed, like the number inside, which is 3, and of course you get 12 plus 12 again plus 3, that will be equal to 24 plus 3, which is 27, which is also 3 cubed. And you can continue this with all the rows below. And yeah, that's essentially it. So that's the video.